an interesting binomial problem there we go. Now, this would not be an interesting binomial problem. What is the probability of getting 4 out of 7 girls if you have 7 children? Right, that's push a button on a calculator. That's not interesting. It's got to require some interpretation. Is it unusual to have 6 out of 7 girls? Is it unusual to reach in a bag of M&Ms and pull them all out and find only 1 out of 30 green if Mars says there should be 16% green? All right. So something that involves explaining to my mother. So that requires some interpretation. Okay, due Wednesday. My advice would be to review your homework in sections. That would be 5.3 and 5.4. Those were the interesting binomial problems. So like I made up what I thought was an interesting binomial problem the other day about the % of female teachers in public school. It's kind of marginally interesting. It's the best I could do at the moment. So you have to do at least that good. Yes?
So we're just writing the problem, we're not actually solving it.
Well, I would recommend being able to solve it, because what I'm going to do is I'm going to take like the top 5 or 6 of problems you guys submit, and I'm going to put them on the test.
No, don't write that.
Yeah. Yep. Okay, so this is a 10-point homework assignment, which is the same number of points a particular section is worth, which makes it a pretty high weight. So don't blow it off. Come up with something. Be creative. You could either look up some interesting statistic in whatever you're like. Anybody have an interesting hobby? You play sports, don't you? What do you play? Basketball. There's some interesting statistics in basketball. You could try and find one that makes a cool binomial problem. I like to ride bikes and brew beer. Sure, I can come up with a cool beer one. Okay. So if you're feeling like a lack of inspiration for this, feel free to sit down and talk to me, and I'll help you come up with some ideas. Or you could just look at something in the book and make up something similar as a last resort. Okay. And the data, the percentage could be real, like my 76% of public school teachers are female, or you could just have an idea and make shit up. Okay? Totally up to you. Just make it interesting. Don't make it too easy, but don't make it too hard either, because we need to be able to solve it. Specifically, you need to be able to solve your own problem. Got it? Okay. Questions? All right. Good luck with that. Have fun. All right. It sounds hard? It's not that hard. So here are some examples. Tom Mooney has lost 56% of all hands at the poker table tonight. Tom plans on putting an end to his losing streak and getting his money back. Consequently, if he doesn't, he won't be able to go home tonight because his wife might kill him. Tom believes that he can win 8 hands if he plays at 10 different random tables, which would win his money back and clear his bad name. Is Tom's way of thinking rational? Why or why not? That's a binomial problem one of my students last year wrote. It's cute, interesting, solvable. It's a little tricky. That's the hardest one here, I think. 72% of Americans sing in the shower. If a sample of 20 Americans is selected at random, is it unusual that at least 8 of them sing in the shower? Why or why not? Okay, it's not just give me a number, it's what does it mean? Okay, so those are some samples people made up. I think most of these are fictitious except for D. I think D is the I think D is the only real one. Oh, Mother's Day. Yeah, the last test was just before Mother's Day, or just around Mother's Day also. So somebody had a good Mother's Day problem. All right, let's do something with a normal distribution. Let's see. Here's one. Let's blow that up a little more. Let's go 150, full screen. Assume the weights of men are normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. Find the probability that if an individual man is randomly selected, his weight will be greater than 180 pounds. Okay. First of all, is this a problem that involves the normal distribution? Yeah, assume the weights of men are normally distributed. Boom, okay, we're using normal distribution. Usually it'll be that obvious. Okay, part A asks us a question to calculate a probability. The question is, does this want me to use the central limit theorem, or is just this a regular normal distribution problem? Is it asking me about groups of people and averaging those groups' weights? Does it say anything about grabbing 20 men or 10? No. So that means there's an individual man, it's just a regular binomial probability. Okay, so what are you going to do here first? You're going to draw a picture of this. So write down the mean, 172. Write down the standard deviation, 29. And draw yourself a cute little bell shape. What goes right in the middle of my bell? The mean, which is 172. Okay. All right, let me get to my notebook here. Here's my bell curve. Right in the middle is 172. Let's see, 172 plus 29 is going to be 101? 201? Right, that's what I meant, 201. So one standard deviation there is about 201. Another standard deviation past that would be 230. On the other side, if I subtracted 29 from 72, 143. And what if we do that one more time? Uh-oh, my pen died. Oh, shit. Stop it. That was weird. This happened yesterday afternoon. I don't know what it is. This thing's getting old. It's about 7 years old now. I want to Control Z that. Okay. 143 and then 114. Now, these are actual weights, right? In a normal distribution. If I were to write down z-scores instead, what's the middle z-score have to be? 0. What's the 201 as a z-score? 1. 230 is 2. The 114 would be -2 for a z-score, and the 143? -1 for the z-score. Okay, so there's z-scores and weights shown on the same scale. All right. We want to know where 180 is. Okay. Is 180 what? In the first standard deviation to the right somewhere? Okay, so let's use a different color, maybe right here-ish. 180 is about there. And what did I want to know about 180 again? If the weight will be greater than 180, okay. So I want to find this area right there. Okay, so the probability, I'm going to call it W for weight, is greater than 180. Does it make a difference if I write greater than or equal to? Yep. Is that going to throw things off? Is there any difference between that and that in a normal distribution? Ooh, good question. Do we ever use the normal PDF? No. Okay, we never use the normal PDF. What the normal PDF it gives us is the height of the curve, which is useless to us. It's a normal CDF. Okay, what about the equal to, or does the calculator ever give us the option to put equal to or not equal to? Doesn't. Let me ask you another question. What's the probability that somebody's weight is exactly equal to 180? It is 0, thank you. That question just like that will be on the test. If it's a continuous distribution, probability of any one number occurring is 0. 1 out of infinity. 1 out of a billion, billion, billion is nothing. Okay, so that's important. So it doesn't matter whether I write it as greater than or equal to or just greater than. They're the same idea. All right, let's erase this. So I bounce back and forth between using a spreadsheet and using a TI. So remember, and I said I'd put this with the test, under the course home, I put an announcement about how to type normal distributions into the calculator. I'm hesitant to give you the picture to go with it, but let's see. We are doing a thing like this, or are we doing like a left or right tail? Or, yeah, and it turns out on the TI, it doesn't matter whether you do a left or a right with a normal. Binomial it matters, but a normal it doesn't. Okay. So the TI says we're going to do the normal CDF, left side, right side, mean, standard deviation. Are you going to write that down on the test? Yeah, so on the test, you're going to write the probability equals the normal CDF. Left side is 180. Right side is 1E99, and that's the big fat E there. Mean and standard deviation, 29, yep. Okay, and from that calculation, what do we get to 3 decimal places? 3, 2, is that what I heard? 391? Anyone else get that? Yeah, okay. So then I would tell my mother 39.1%. She can usually handle 0.1, 1 decimal place in a percent. Maybe not. I might have to tell her 39%. It's a bad day. What does that number mean? What the hell does 39% mean? My mother doesn't get the whole right tail thing. There's a 39% chance that some randomly picked male will have a weight above 180. Yeah, so let's write that down. I'm going to use the word exceeding. I haven't used it in a long time. Is that okay? You didn't get that number? Uh-oh. Yeah. Let me whip out my... So let's turn you on. So let's see. Distributions, option 2, normal CDF. Lower bound is 180. Upper bound, so then on the older one I want comma, but you probably have the same screen, right? So 1 above the comma is the E, 99. Mean is 172. Standard deviation is 29. And I get 0.391.
Did I use the wrong E? Is that a bigger E?
Oh, that looks like the same E. Huh. And you're getting a different answer? Oh, shit. I do have a different answer. Okay. Negative 60. Weird. Okay, you have a problem. We'll fix it after class, okay? Sorry, I don't know what's... So anyone else having calculator troubles? We need to make sure we're on the same page in calculations. Oh, shit. It's the wrong E. Okay, so we got to find another E. Yeah, which E did you pick? Oh, the letter E. Oh, yeah, not the green E. Oh, this is super important. Okay, so calculator stuff. So, you know there's an alpha key? That lets you type letters. Like you could write a word. I could write Gary on there. The calculator also uses those letters as storage places. You can put numbers in there. And so like on my calculator, if I say, what is that green E? My calculator thinks it is 0.101-ish. I don't know why. Yours might think yours is 0 or 10. I can put any number I want in there, like 7's a nice number. I could take 7 and, oops, store it in the letter E. Oops, that's not the letter E. Where'd you go? And now the calculator thinks that green letter E is 7. That's different than this E right there. Notice it's a little smaller, a little sharper. Okay. What that means is times 10 to the power. Okay, so it's a weird engineering notation. If that's throwing you, then instead you could use above the log it says 10 to the x. So alternatively, if that E is going to be a problem, oops, let me clear that. What I could do for the normal CDF is I could just write 1 times 10 to the power 99. Close the parentheses. That's what I really mean. That E is kind of confusing. I'm not happy with it anymore. And I'll still get that same number. Okay. All right. Whew, solved. That was scary. All right. Let's see. Exceeding, that word's bugging me now. I'm going to change it. How about instead I write, we'll have a weight of at least 180. Or should it be at most 180? At least? Yeah, it should be at least. We got to get the whole at least, at most thing. That's another common little mistake we make with these, and I mess it up once in a while too. It's the same problem I have with left and right. So if I have at least 25 cents in my pocket, that means I should have that or more. Uh-oh, my daughter took my money. Okay, oh well. I have at most 25 cents in my pocket. Is that true? No? I have at most 25 cents. I have 25 or less, and I'm pretty sure I have less than 25. Yeah, nothing in there. Okay, let's look at the next problem on this test. All right, find the probability that 20 randomly selected men will have a mean weight that is greater than 180 pounds. Ooh, a group of 20 was selected, and we're looking at the mean. We're condensing the information of all 20 people to a single number. We're narrowing the information. What does this seem like? The central limit theorem. The central limit theorem, yeah. Whenever we take a group and we narrow all that information down to the mean of the group, that's the central limit theorem at work. Okay? That's the central limit theorem at work. All right, were we given information about the subsamples, or were we given information about the population in the beginning? Population, yes. Okay, so now we've got to sort out what the hell all this means. Okay, I'm going to steal that text into a screen and see if we can sort it out. New screen, steal this line right there. And that's kind of big. Can I reduce you a little bit so you fit? Okay, it fits. All right, find the probability that 20 randomly selected men will have a mean weight. Okay, so this is the central limit theorem. That tells me right there to use the central limit theorem. Central limit theorem. Central limit theorem says a couple of things. It says that n should be greater than 30 in most cases. Do we meet that criteria? But I gave 2 exceptions. Except when? Anybody recall? There's a couple of times I can kind of ignore that n being greater than 30 idea. If the population is uniform or if the population is normal, then you can kind of get away with it. So except if population is, and the uniform is a little arguable, but it works most of the time, or normal. And relatively normal is good enough, actually. All right, so we meet this condition right there. So we didn't meet the 30, we didn't meet the uniform, but we meet the normal population to start with. Okay. Central limit theorem says then that, oops, premature, that the mean of the means and we have one of them up there, is about equal to the mean of the population. And usually the book just calls it mu. What does mu represent? The mean of the population. When we're talking about the mean of the samples, we'll use mu with a sub little tiny x bar. Also says that the standard deviation of the means, is about equal to the standard deviation of the population, but tweaked a little bit, dividing by square root of n is our tweaking factor. And then usually the book does not write the little p there. What were we given here? The standard deviation of the means or the standard deviation of the population? Yeah, we were given the population. We were told that, switch colors here. We were given that the mean of the population was 172 and the standard deviation of the population was 29. But now I'm doing a calculation based on these 20 men. So based on those 20 men, I now have to use this and this as the standard deviation and the mean. Now the mean's no big deal. They're the same theoretically. But the standard deviation is tweaked. So here's the new information. For 20 men's mean weight, that's still going to be 172. Oops, wrong order. But the standard deviation for the mean of the men is going to be 29 divided by the square root of 20. That's the thing I have to change here. Can somebody whip out on a calculator what is approximately to one decimal place 29 divided by the square root of 20? 6.5? Okay. So my new standard deviation for groups of 20 men is 6.5. I'm looking at the mean weights of 20 men. So now when I consider my picture here, 172 still goes in the middle, but one standard deviation to the right is now 172 plus 6.5, which is 178.5. And if I add another 6.5 to that, that's going to give me what, 185? Yeah. And I want to know what is the probability that their mean weight is greater than 180? Is that right? What is the probability that they have a mean weight that is greater than 180? Okay. So I need to figure out in this picture, what is the probability that X bar, or I said W bar, right, the mean of the weights is greater than 180. So 180 is going to sit right over here-ish, right? Right next to the right of, actually it's a little farther than that. Let's clean that up. It's more like right there. That's my 180. Am I going to the right or the left here? To the right because of the greater than, yeah. So I want to know what this area is. Write down what you think you're going to type in the calculator and then type it. Normal CDF or PDF? CDF, never the normal PDF. Left side is 180. Right side is infinity. Mean 172. Standard deviation 6.5 or 29 over the square root of 20. Depending on which number you use, your answers will vary slightly. I'm going to type 29 over the square root of 20.
What does that say at the top there?
10 to the 99th power. That's the calculator's version of positive infinity. All right, so the only thing that's changing is my standard deviation. I'm going to divide that 29 by the square root of 20. Close my parentheses, enter. So I get about 11%, 10.9-ish percent. If I use the 6.5 instead, my answer will look just slightly different. So let's just compare 6.5, close parentheses, delete, 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 enter. 10, yeah, to the nearest tenth of a percent, they're the same, so that's okay. But again, if we round prematurely, our answers will be a little different. That's not a huge deal. So I get, this is about 10.9%. Okay, now what does that number mean? 10.9%, what does that mean? Yeah, that the average weight of 20 people is going to be greater than 180. Okay, so why would I care about that? Well, maybe I'm running a fishing trip, and on the side of the boat it says average weight cannot exceed 180. What's the probability that the average weight of a group of 20 men will exceed 180? 10%. Okay. Is that a big risk? Will I need to look carefully? Like if they're a bunch of football players, am I in trouble? Soccer players, maybe? Well, maybe, maybe not. Basketball players? That might be a problem, right? So it depends on the group, but your average person, there's a 11% chance that they're going to be over the weight capacity of the boat, and if they're drinking, that's trouble, right? Balance is hard enough on a boat when you're sober. Okay, so again, this is 6.5. The big deal here is whether we're looking at a summarized group of people or a single person, depending on whether we tweak the standard deviation. Yes? Oh yeah, names for those things. Yeah, give me those quick before you run away. And then you got to hand in those papers too. All right, let's stop the broadcast.